Well, I'm very pleased to have this opportunity to present to you the talk by Professor Swanhild Bernstein from Freiberg, Germany. And today she will speak about the Dirac-type operators and applications. Please, Swanhild.
Thank you. Well, I have to thank you all for the opportunity to give this presentation. I was a little bit unsure what I should do. I mean, I have no idea what you are usually interested in, what your fields of research. So I tried to give somehow a little bit an overview of something I have done in the last years. And I will start. Yeah, I will start. Nice. Usual problem. Okay, now we can start. This is more or less an overview. I will start with some more or less well-known things about Clifford algebras and Clifford analysis. I would like to say something about image processing and optics. Where are the applications of the operators? And then some kind of generalized operators, which have more or less the same behavior as the known operators, but which are some kind of different to the well-known and why we are looking for them. Then I will say some words about function spaces of Clifford-valued functions, fractional operators, and that these fractional operators will lead to some specific function spaces. So we start with the easy thing, Clifford algebras. We all know numbers of some type, and they have properties and some have not good properties. So the Clifford algebra may be seen as a generalization to higher dimensions of the norm division algebras of the real numbers, complex numbers, and quaternions. We know that there is a huge theory of real valued functions, complex valued functions, and we have generalizations into the quaternions, and we can further generalize it into Clifford algebras. The multiplication in a Clifford algebra is non-commutative, but still associative. This is different to the octions, which are also numbers, but which are not in this line of Clifford algebras. Unfortunately, there are zero divisors, and you cannot just divide by a Clifford element. What I usually use is a specific Clifford algebra, the so-called Clifford algebra CL0n, which is generalized by n, generated by n elements, E1 to En. Sometimes we will that also identify with the Rn. And then we have specific non-commutative multiplication rules. First of all, for these generating elements. Ej square is equal to -1. The idea is to have a generalization of complex numbers. And of course, the multiplication is non-commutative. Ijk plus Ikij is equal to 0. We will have a conjugation, which is also an anti-involution. Bar Ej is equal to -Ej. And the whole algebra is spanned by all possible products of generating elements. So you not have just E1, E2, E3, En. You have also the products E1, E2. You have E1, E2, E3, or E2, E3, E5, A9, whatsoever. And you get a basis with these more or less arbitrary elements EA. An algebra has an identity. Okay, questions? The algebra has an identity element for what we write just a number 1 or also E0. The algebra can also be complexified. This means more or less we have complex coefficients. These are more or less everything what I need to know about Clifford algebras. Then the Clifford analysis more or less is going to introduce a so-called Dirac operator, which is related to the Dirac operator in physics and is just a first-order partial differential operator, where the partial derivatives are combined with the generating elements. Different versions are possible, but the interesting and in some sense important property is that more or less d squared, the Dirac operator twice applied, is equal to the Laplacian. We have a fundamental solution which helps to generate all necessary operators. We have the Cauchy integral. The Cauchy integral allows us to describe monogenic functions, and the monogenic functions are the null solutions of the Dirac operator. You have to make a difference between left null solutions and right null solutions, but the fundamental solution is a left as a right solution to the Dirac equation. Then based on this fundamental solution, we have, of course, the Cauchy integral, the singular Cauchy integral, also related to the Hilbert operator, and the Hilbert operator is nothing else but the linear combination of the wreath transforms. Don't mix it up with the wreath potential. It is a wreath transform. And then we are more or less in the game for basic Clifford analysis. You know from complex analysis, where you consider null solution of the bar operator, that you can have a Hardy decomposition into monogenic function inside or outside, or in the simplest case for the upper and lower half space. And here we have a similar situation. We can decompose functions into monogenic functions in the upper and in the lower half space. And if we go to the boundary, we have a decomposition of the boundary values in the boundary values of monogenic functions in the upper and lower half space respectively. And this theory more or less says that. Yes. If you have an LP function and on Rn was the boundary. Yes, that's in the middle. That's the boundary. You have a function on the boundary. Then you build up the Cauchy integral, and you take the non-tangential limit to the boundary, in this case Rn. Then you can decompose the boundary values in boundary values of a monogenic function in the upper and lower half space respectively, and you have a Hardy decomposition on the boundary, and of course a similar decomposition for monogenic functions in the upper and lower half space. This is more or less what I would call basic Clifford analysis, and you have the Dirac operator and associated integral operators and this decomposition. This decomposition can be generalized to domains with smooth boundaries, but also with Lipschitz boundary. Now for the applications. Well, the applications somehow came to me because when I was in school, I had a friend and she studied physics, and in physics she specialized in optics, and after 20 years we met each other and we figured out that we have something in common, that we are interested in mathematics and physics. And the first interesting observation for us was that there is a relation between what you can get in physics if you measure it, and you can have a similar result if you calculate it using wreath transforms or wreath kernels. So what you see here is that the wreath operators are filters. What is done? You can have it measurement with lenses, and you will see that you have a filter that takes the vertical or horizontal lines out of the image. The image, these are lines and the number 5. And you can see one experiment extracts the vertical lines and the other one the horizontal lines. A and C are measured with optical measurements, and B and D are just calculated with the wreath kernels. So you can more or less do a mathematical experiment which is equivalent to a physical measurement. And we stick with that. Our wreath transforms are important, and they are important also for other things. If you want to do signal processing, well, the easiest signal is something you can hear. Yes, if you hear me, you have a 1D signal. If you see me, you have an image, you have a 2D signal. A 1D signal can be characterized by an amplitude and by a frequency. This is more or less the easiest way to call it in time frequency analysis. Then it turned out there's a very ingenious idea is not just to consider a signal which might be A of t, this is the amplitude multiplied with a cosine wave, cosine omega t, but to look for an analytic signal. An analytic signal is f plus ihf, so you add imaginary unit I multiplied with the Hilbert transform. So what you get are more or less boundary values of an analytic function in the upper half space, and you have some nice properties of this construction. You can, one good thing is this Petrosian identity, which tells you that under some circumstances, you can obtain the same amplitude for the analytic signal as for the signal itself. And the reason for that is that the Hilbert transform of the cosine function is the sine function. Then you have a quadrature formula, and you can see that the amplitude and the envelopment of this signal look very beautiful. These are good properties of this analytic signal. And you have also some mathematically, physically important properties of this analytic signal. For example, the original signal is reconstructible from its analytic signal, particularly the real part of the analytic signal is equal to the original signal. So the question is if this works in this way by adding I times the Hilbert transform of the signal to obtain an analytic signal with good properties. Could it work in higher dimensions? So if you go into higher dimensions, where to look for? Yeah, well, if I ask you, I guess you would say more or less the same as people did. Okay, there is a complex theory, but you have also the theory of several complex variables. And we would answer, okay, you can also look for Clifford analysis. And these are more or less the answers. One answer is indeed called the analytic signal, and it goes back to Hahn. He tried to look for something in higher dimensions. Of course, you need more than one part, and what he did was more or less to generalize the idea that your analytic signal is a convolution with delta of x plus I over pi x. So you have a Hilbert transform. And he more or less did it twice, once in x and once in y. And if you calculate what this means, then you have your original signal f of x, and you have 3 parts. You have these partial Hilbert transforms given by I over pi x and I over pi y. These are these 2 parts. And you have something, this is called the total Hilbert transform, which you obtain from the multiplication. These three parts are added to this original signal and you get the analytic signal. The hard part is you cannot reconstruct the original signal from the analytical signal. Now the idea by Bülow was first of all to look for something else than complex theory, more or less to use quaternions. I, J, K are quaternions, and he introduced two different complex units. So he has one unit I and one unit J, which is good for quaternions, which also would be good for bicomplex numbers. And his idea was more or less to do exactly the same, but the construction now invokes the signature functions in the Fourier domain. Because if you take the Hilbert transform and Fourier transform it, then you will get something like the signature of omega. This is a good step, but you can see none of the approaches yields the perfect envelope. And so people looked for other constructions. Bülow was a member of the research group of Sommer, and the other student of Sommer, Felsberg, he found what is nowadays celebrated as the monogenic signal. For the monogenic signal, you can see that he went away from the Hilbert transform and used wreath transforms. So you have these three wreath transforms. They are combined with quaternionic units, but you can also take a Clifford vector, no problem. What you get in this sense are again related to monogenic functions. This is the point of the construction using the wreath transforms. And you have also the opportunity to rewrite it in a polar form. Yes, just do it for the quaternions, do it for a Clifford para vector. Then you will see that you have an amplitude. And you have an exponential which consists of a unit vector multiplied with a scalar function. This unit vector is called the local orientation, and phi is just the local phase. So you have a similarity between the representation of an image, not of an image, but of a signal, a 1D signal by amplitude and phase, and now you have an image that you can represent by an amplitude, of course, local orientation and local phase. When you have a little bit more, you have this rotational invariance. This just comes in because the wreath transforms are used. Yes, here are the uniqueness of the wreath transforms. If you have such an n-tuple of bounded transformations, then they must be wreath transforms. If they commute with isotropic dilations, and you have this property of the rotation. This characterizes the wreath transforms, and this is already figured out by Stein. Now, has it an impact? And the answer is yes. Here you have a standard gray valued image, the so-called Siemens star. You can see it is very nice symmetric. These colored things, these are false colors. They are just made to represent numbers. But what you can say is that the different transformations lead to different results. Specifically, by C and G, you see a difference between the monogenic orientation and the analytic orientation. The monogenic orientation preserves much more the symmetry. With this analytic orientation, it is much more distorted. This has to do with these Hilbert transforms used by Hahn, they have not this rotational invariance property. This is only by the wreath transforms, and you can see it in these calculated images, these special properties of the signal. A lot of people nowadays use these monogenic signals and also the representation of a signal with amplitude, phase, and orientation. and you can get a lot of investigations in that direction. From a mathematical point of view, now we want to go away from the wreath transforms. We want to have wreath transforms which are similar. So what the idea was to say, okay, we have considered Dirac operators, Dirac equations, maybe you can also consider Cauchy-Riemann equations, then you have also a partial derivative with respect to x0. But the interesting thing is that your Dirac operator can be factorized in the absolute value of the Dirac operator, which is nothing else as the square root of the negative Laplacian in the Hilbert transform. So the idea is to say we replace our Hilbert transform by something which has similar properties. For example, if you take the Hilbert transform twice, then you get the identity. Such properties should be preserved, but with everything else, we are more or less free. Now you can take that to make something that is called quasi-monogenic. You can calculate the semigroup connected to this generalized Dirac operator, and you will see that more or less the whole theory for the Clifford analysis is similar. We have specifically this Hardy space decomposition in the upper and lower half space, and for the moment the question is why we do it. Well, one answer will follow, and this is the so-called linearized wreath operator. The next slide will show it why I was interested in that. Here is how people could construct this so-called linearized wreath operator. What is actually linearized? Well, if you remember the Hilbert transform and the wreath transforms, if you look for the Fourier symbol, then you have just omega over the absolute value of omega. So this is the starting point. How can I decompose that? I put it in a polar decomposition, and what I get is this function theta of omega, and theta of omega is just the arctangent 2 of omega. No problem with this. It has to be the arctangent 2 because you have to choose different values if you go around in the unit circle. Now what here the idea is, you want to have something, this is invariant concerning shears and not rotations. So if you go from the rotational symmetry to the shear symmetry, you have to work with cones. Instead of these 4 quadrants for the unit circle for the arctangent standard function, now you have these cones. It looks a little bit weird, but what you are actually do is nothing else. You just drop the arctangent, you just take omega 2 over omega 1. This is also this linearization. Therefore, the name comes. You linearize the arctangent function, and now it has to fit with these cones. It just makes it a little bit weird how it is defined. But the idea is replace the arctangent function by its linearization. And what you get is a linearized wreath transform, where you just define your theta of omega fitting these specific cones. Then it has more or less the same properties as the standard Hilbert or wreath transform. If you take the square, you still have a symbol where you can look at it. It is more or less the same, but it fits perfectly these cones because, it commutes in some sense with shears. Yes, here's the definition. Then you have a shear operator. You can have shears in different directions. This is one direction. And you look for the cones, and you can see that if you apply these linearized wreath operators to g of shear x, it is the same as if you apply the wreath operators to the function at the shear inverse to x. So this is called a shear invariance, and this is similar to the rotational invariance of the classical wreath operator. You have an additional exponential in front of it. This is not the case for the classical wreath transform, but here you can, the idea was to look for shearlets instead of wavelets, and there you needed such an intertwining property. And we could get it also for shears, and it can also be generalized into higher dimensions. And well, the connection, if you make it a Dirac operator, then you have, of course, that the Dirac operator is the absolute value of the Dirac operator combined with the Hilbert transform. And what I did is more or less looking for the Fourier symbol, and you can see that it is a little bit transformed if you take the linearized version, and you can also see these cones in this picture. Well, I called it the psychedelic Dirac operator because if you look too long at it, well, it has some kind of psychedelic effect to you. And it is a deformed theory, but it goes more or less along the same lines as the classical Clifford analysis. Therefore, the theory to these functions are called quasi-monogenic. Function spaces. You may say it is quite simple to have function spaces for Clifford valued function. You just look at each component, and the component should have some properties. Well, this is true, and it is not true, because if you have a Clifford valued function, you want also to say something about these functions in this context, not just looking for the components. Now, there's an interesting result. It depends on the Hilbert space, on the definition of an Hilbert space with an inner product. So we have an Hilbert space with an inner product, which is also an associative Banach algebra with identity E. Then you have the standard norm, and you can say the norm of a product can be estimated by the product of the norms, and the norm of the identity element is equal to 1. Such an algebra is called Hilbert algebra with identity. And Ingelstam proved that the real Hilbert algebra with identity is isomorphic to the real numbers, the complex numbers, or the quaternions. This is bad for us. Because if we want to have a working norm, we need a norm for the Clifford algebras, and of course, we want to have submultiplicativity and the triangle inequality. If you don't have that, you don't have a good absolute value, because these inequalities will lead to Hölder inequality, Minkowski's inequality, and Young's inequality. So what is the solution for that problem? It is already described in the first book, Clifford Analysis, by Prax, De Lange, and Sommen, that the key point is this factor in front, these 2 to the power n. If you say that you have an element of the Clifford algebra, say lambda 0 plus lambda 1 E1 plus lambda 1 n En plus lambda 1 2 E1 E2 and so on, you give it an inner product or scalar product just if you multiply lambda bar with mu and take the real part of that and multiply with 2 to the power n. Then you have a corresponding norm, you have a real Hilbert space, and it is at the same time a Banach algebra. And you may wonder why. Is it possible? Because the slide before said it is impossible. But the point is, if you calculate the norm of the identity element, it is 2 to the power n½ and not 1. So you are, this 0 has to be a 1. 2 to the power n½ unequal to 1. So you have a valid structure for your Clifford algebra. And with that, you can construct in an easy way LP spaces, for example. Because all what you need is a good absolute value. And if you have that, you can prove Hölder inequality, Minkowski inequality, Young's inequality. You have typical embeddings, but it won't work if you don't take the factor in front of it. And what you also get is this norm is equivalent to a norm where you can prove that each component is an element of the LP space. So even it looks a little bit ugly, this 2 to the power n in front of it is important. Operators, fractional operators. It's a good question. If you look in books for the Fourier transform and you look up the fractional Fourier transform, you have an awful thing there and you have no idea how the hell could they get it. But if you look for a general theory, then you would say, okay, what should we have? Of course, we want to have that our operator depends somehow on a parameter. If the parameter is equal to 1, then we want to have our transform. -1 should be the inverse transform. 0 should be the identity operator. And what we would like to have is some kind of semigroup property. And we would like to represent our transform in closed form that we have some kernel. And now you can do this in a very easy way if you have a serious representation of your transform in some kind of a Hilbert space. Then you will have eigenfunctions and you will have eigenvalues, and you can use that to construct your fractional transform. And now, of course, we would like to have our Dirac operator. Our Dirac operator is decomposed as before in the square root of the negative Laplacian, and we take it to some power alpha. Well, this is the classical fractional Dirac operator. And we will have to use some kind of a fractional Hilbert transform. Then we can combine both and we will get a fractional operator depending on 2 parameters. We will use the standard Fourier transform and we are looking for Fourier multipliers. This is nothing special, this is standard theory. If you take the Fourier transform, then you may have a linear operator. If you transform it, you have just to multiply with the so-called Fourier symbol, Then, if you look for the Laplacian, you will see that you can do some decomposition and you have the classical Fourier symbols for the Laplacian and for the Dirac operator. And you can solve the Cauchy problem with an associated semigroup. Here you have the semigroup associated with the Laplacian. Although nothing important. What is important, if you want to have something about mapping properties, you need some properties of the multiplier. You are in the Fourier domain, and the multiplier more or less tells you what are the mapping properties of your operator. If you look for a Sobolev space, then you know that the norm of the operator of the function is defined for the Fourier transform in Fourier domain, And if you apply the operator, it means the multiplication with the symbol, and so the properties are given by the multiplication. There is the well-known Hörmander-Michelin multiplier theorem. They more or less tell you in the simplest way when you have a multiplier in LP spaces. This gives also rise to the so-called modulation spaces, where you can consider function more appropriate. But what we have here, we want to say the symbol is important, the symbol is a multiplier, and you can work with it. Now to the construction for our fractional Ries-Hilbert transform. This Hilbert transform is made up from the Ries transformations, and our Hardy space decomposition more or less tells us that we have these two decompositions, and it tells us that the space can be, that the spectrum consists of the number 1 and the number -1. The 1 is in front of the first projection, this is 1/2 I plus h, and -1 is in front of 1/2 I minus h, this is the other projection. Now to get a proper fractional operator, you have to take just the power alpha of the eigenvalues. Of course, 1 to the power alpha is still 1, but -1 will be considered as a complex number, and so it becomes e to the power minus I pi alpha. Then you recalculate everything, and you can get a Hilbert transform H alpha, which has this factor e to the power minus I p half alpha, cosine pi half alpha I plus I sinus pi half alpha h. You can also get rid of this factor in front of it, and you have another fractional operator. The interesting thing is that this construction, which I made here for this Ries-Hilbert transform, is done in optics. In optics, it is done for the Hilbert transform in the classical sense, and the motivation was that you can interpolate between the near and the far field. So they also looked for such fractional operators. This is more or less the generalization, just in higher dimensions. Now here I will nothing do but use this operator. Yes, here are some examples. Well, this is not really insightful, but to give you some idea how it works. Of course, you can obtain different operators by different parameters. You can have an identity, you can have interesting looking objects. They are just in between the identity and the Hilbert operator. Now this is the idea. Back to our fractional Dirac operator, which consists of a fractional Laplacian and the fractional Hilbert transform. Now if you look for the Cauchy problem, you are used to get some kind of a semigroup. The solution can be described by the aid of this semigroup, and if you look for it in Fourier domain, you will get a multiplier. The sigma alpha theta is the multiplier, which gives you the formal solution of the problem. It looks a little bit awkward. You have so many exponential functions, but this comes from this Ries transform and is not a surprise. If you go through it, you will figure out that you have terms, they are easily to estimate, because you have something in these parentheses that behaves like a complex number. So you can say, okay, this is bounded. And then you have the exponential in front. E to the power minus t absolute value of xi to the power alpha and this cosine function. Now it is not so difficult to see that if theta is between 1 and 3, then you have no decaying. You have instead that your function is growing. Now, if you have that as a multiplier, the question arises, what are the mapping properties? What are appropriate spaces for such a problem? And interestingly, here it is done together again. You can see it is a combination. On the axis, you have more or less the operators itself. And you can see that for theta between 1 and 3, you have the interesting part. The red line is more or less if you choose alpha equal theta. Then you have this red line. This interpolates between the identity and the Dirac operator, but you have this whole collection of operators. And of course, sigma alpha theta belongs to the formal solution of our problem. Now the spaces, yes. Well, the first thing looks a little bit ugly because I found it has to do with Berling's generalized spaces. First of all for distributions, but also for other things. The first thing is you need some kind of weight. Yes, we have this exponential function and we want to make it a weight. A weight in that sense, introduced by Triebel, is just a non-negative function which is radial and it should be a continuous concave function. As a result, you have a restriction of our alpha between 0 and 1. Because afterwards you don't have a concave function. Then the weight at 0 should be 0. It should have some behavior at infinity. This is the second condition, that the integral from 0 to infinity omega of r divided by 1 plus r squared, the integral has to be finite, and it should be possible to estimate it with these logarithmic functions. First of all, if our weight is subadditive, then you can take the exponential of it and you get something submultiplicative. This is the connection between our weight, which is subadditive, and the exponential of it. This includes standard weights. For example, what you have for a Sobolev space. And of course, it is important for me that it more or less restricts our alpha to the range between 0 and 1. If you are not in this range, you don't have all good properties. Then these Berling spaces are more or less saying you have a weighted space. The space is made of an integral of the Fourier transform, and instead these Chinese brackets, here you have an exponential function with this weight omega. And the parameter lambda and the spaces are more or less parameterized by this lambda. Lambda has to be a positive number. Then you more or less get the same as with the Sobolev spaces. Yes, you have a Frechet space, but it depends now on this exponential. Then you can consider generalized Schwarz spaces. They are usually helpful if you want to differentiate and multiply. Here it is based on this exponential. And then we get more or less what we are looking for. I already said it is more or less nothing else but a Sobolev space, where you have the exponential function as a weight. As if you put in the Chinese brackets, instead of the exponential function, you would have a Sobolev space. This is the definition, and this fits perfectly with our operator, because the symbol of our operator more or less says that the weight omega should be the absolute value of xi to the power alpha multiplied with the cosine. Of course, you can have something equivalent to that, But if you take that as norm, you can describe the mapping properties of the operator. If you have a function from L2, then the solution of the Cauchy problem for a specific value of t will be in some of these generalized Sobolev spaces of these Berling spaces. So to summarize, if you consider a fractional operator, you have the interesting problem to look for more or less exotic function spaces. But it is at the end of the day not so exotic. You just replace the standard weights here by some exponential functions, and you are in the game. You can also look for other types where you weaken the conditions. You say that your weight is just so-called V moderate, then you lose some properties, but sometimes it is also more general. You have a connection to the Gale-van Sheloff spaces, because also Gale-van Sheloff spaces go in that direction, and you can construct now a lot of different types of modulation spaces where you take, instead of the standard weights, these generalized weights. And if you are interested in these things, then you have, of course, classical papers on the Fourier multipliers by Miyachi. You have an interesting paper by Benji, Kreshnik, and Okotiu and Rogers on unimodular Fourier multipliers. This is not the case for these fractional operators. You have Gale-van Sheloff spaces and pseudo-differential operators. These are the papers by Theophanov and co-workers. If you are just more interested in these exponential weights, the paper by Kreshnik and Zimmermann is advisable. You can have some ideas about the time frequency analysis for the Dirac operator in this recent paper by Trapasso. And there are also some papers of mine which have to do with these fractional Dirac operators and their applications. What can we do? Well, we could look for a time frequency analysis for these fractional Dirac operators. Of course, we can solve some Cauchy problems for these operators. An interesting question is that you have also important operators. They are out of scope for these specific setting. Because if you go beyond alpha equal to 1, you can still construct weights, but these weights don't fulfill the standard properties. But these are interesting operators, the Schrödinger equation or also Airy equations, but then you have a problem with the function spaces. You can try to generalize it for Clifford valued symbols. An interesting construction are also the time frequency localization operators. If you don't know, you can look in this paper by Theophanov and co-workers. They wrote about these time frequency localization operators. They are already introduced by Dubschis. And an interesting observation is that you can have difficulties with your weights. It is a result by Kreshnik and Zimmermann in this mentioned paper on Hardy's theorem and the short-time Fourier transform of Schwarz functions, that if you have a multiplier that is bigger than c e to a and absolute value of that square, what it means is explained in the paper, then the corresponding modulation space contains only the trivial function. And you don't see it from the construction, but their Hardy's theorem implies that. I hope I didn't do too much. It was too overwhelming, but I have to say thank you for your attention.
Thank you very much, Swanhild, for a very interesting talk. Thank you. So now it's time for questions.
There are questions. Thank you very much for your interesting talk. So my question is the following. There is some calculus of the pseudo-differential operators in value on the Clifford algebras, which by means we can obtain the results, some general results concerning the more general than the Dirac operator or other operator in the more general approach to these things.
Well, in fact, yes. In the moment, I was just interested in these fractional operators. And, well, the interesting observation for me were these Berling spaces. Of course, you can also define general Clifford-valued symbols, and then you can discuss these operators. The more interesting question is if you really get something new.
Okay, thank you. Another question: what I would like to know about the Riemann-Hilbert problems, and one side Riemann-Hilbert problems, two side Riemann-Hilbert problems in the Clifford analysis.
There are well. The problem has its importance because the Riemann-Hilbert problem is a classical important problem. The hard part in Clifford analysis is that you have a non-commutative structure. So there are some papers on this topic, but you cannot overcome the problem with this non-commutativity. Because if you multiply to analytic functions, to complex analytic functions, you get an analytic function. If you multiply to monogenic functions, you get a new function and you know nothing. So this makes it more complicated to discuss a Riemann-Hilbert problem, and similar to the complex case, well, I wouldn't say that the solutions that are obtained are, well, they are not the same as in the complex case, and the results are much weaker.
Yeah, okay. There are quite a few papers on this subject, including the papers by Swanhild Bernstein.
Okay.
So this is, yes.
So it's interesting the Fredholm property of the Riemann-Hilbert problem and something like that.
Sorry, Vladimir, I couldn't hear
okay.
Your last comment. Yes.
Okay, thank you very much.
Okay. If there are more questions, please. Swanhild, may I ask you a small question, more or less on slide number 14, I think. You compared monogenic versus analytic signals. In which sense? I didn't understand. What is this comparison?
Well, we have to look at the signal. Here you have the analytic signal, and this is more or less a complex number.
Mm-hmm.
Yes, and for this complex number, you can interpret in polar form. Then you have a phase and you have an amplitude. And you can also define an orientation. The orientation is in that part also a vector yes. Of these partial Hilbert transforms. For the monogenic signal, you can write also a Clifford number in a polar form, and you have these three quantities: the amplitude, the local orientation, and the phase. And now it is just a calculation. What you do is you calculate the specific Hilbert transforms, or you calculate the specific wreath transforms, and then you can calculate the corresponding phase for the monogenic function or for the analytic function. The same is true for the orientation, and you can take the phase-weighted orientation, then you have the product of the orientation and the local phase. And this is just done. You have one image. This is, oh, I forgot to put in here. Well, it looks more or less like A. This is the amplitude. This is the Siemens star. I'm sorry, there should be also an image of the Siemens star itself. Mm-hmm. But it looks more or less like this amplitude, not so different from that. And then you calculate the phase. The phase is an angle. And you can see that it is different depending on what you calculate. But what you also see is that the rotational invariance of the monogenic functions, because they are based on the wreath transforms, is also revealed in these quantities calculated. The monogenic phase gives a similar picture. It is okay. Each of these quantities is calculated at each point of the image. So each color gives a value of the phase, of the orientation, and also of the phase-weighted orientation. The same for the analytic phase, the analytic orientation, and phase-weighted orientation. Again, just a product. So what you should see in all these images is more or less that the structure is preserved. But the preservance of the structure is more or less perfect if you have a rotational invariance. Well, which is not such a big deal because the Siemens star is perfectly symmetric. Yes, it looks like this monogenic amplitude. So it is more or less symmetric. But you can, of course, calculate these analytic quantities, and you see it is much more depending on the quadrant than it is rotational invariant. And this has to do with the construction. Wreath is rotational invariant, the analytic signal not. But it has a strong emphasis on the quadrants like each Hilbert transform. Because if you look at the Hilbert transform, you know that the Fourier transform of the Hilbert transform is 0 for negative values and 1 for positive values. So if you go into the quadrants, you have it reflects the application of the Hilbert transform. Is it a little bit clearer? Maybe, okay.
Okay, more questions?
Thank you very much for interesting talk. It was really impressive that you obtained such interesting results. So if it is possible, I can ask one question. Was the reason of this generalization was to obtain of improving filters for your example which you provide in the first part of your talk?
Yeah, well, the starting point was to say I need a wreath transform, whatever it is, that has this invariance, this commutative properties with shears and not with rotations. How can you get it? So, and well, if you look for the wreath transform, you have it here. This is the uniqueness of the wreath transform and this property C. this property C for all rotations, you have these invariants. This is nice, and this gives also the nice pictures. But what happens if you replace the rotation by shears? What would be an appropriate operator? This was the starting point. Can you get such a property C for shears and then construct such a wreath operator?
Okay, I see. Thank you very much.
And the solution was more or less to say, okay, instead of arctangent, you just take W2 over W1. And a little bit more because also the arctangent, well, you have to make it fit. That was the starting point, yes. Looking for the invariants.
Okay, thank you.
Thank you. So if there are more questions, please, or comments. So if not, then thank you very much, Swanhild, once more.
Thank you for listening.
No, it was very interesting indeed.